Together with my colleagues Adavant and Ariant, we will present our project. It is an extension of the word model and it is called hierarchical planning with end-to-end JEPA word model. LeWord is a stable end-to-end JEPA word model which contains an autoregressive error for long horizon. The idea to solve here it is add a hierarchy on top of the frozen LeWord model. In fact, we will add a macro action encoder and high-level predictor with two nested CMMPC, and we will obtain an hierarchical, reward-free, task-agnostic, single GPU model. We found that hierarchy never beats a flat, and the bottleneck is the planner latent cost. We use four datasets: two-room, push-T, cube, and Richard. As a metric, we use success rate, which measure the success to arrive from the initial state to the final state using certain budget.
As Florencio mentioned, there are two new modules, an action encoder that compresses primitive action into a latent macro action, and a high-level predictor that predicts a future waypoint from a current state and macro action. We initially trained with just an MSE loss similar to Levol model, but that differs from how we use the model at inference. So we trained two losses to close that gap. First, an autoregressive loss on the high-level predictor. MSC is a simple one-step teacher forced, so the model never sees its own mistake and errors compound at test time. So we fixed this with scheduled sampling. During training, we gradually feed the model with its own prediction, so it's trained the way it actually runs. A second is a moment matching loss on action encoder. The planner samples the macro action from a standard Gaussian, but nothing constrained what distribution the action encoder learns. A mismatch makes the planner ineffective. Thus, this particular loss pushes its output to zero mean and unit variance matching the planner's prior. Throughout our model design and evaluation loop, we chose a simple two-room dataset where we fixed all the planning configuration. With all these changes we discussed, we were able to achieve 82% of success rate. And next, Ariant will discuss about the analysis and comparison with Levol model on different planning configuration setups.
Our headline result is a -1, and that's the interesting part. Across every goal offset on both environments, the hierarchy never beats flat level model. But the two environments fail very differently as the goal moves away. Two-room collapses, it falls flat from high 80s down to 12%. The hierarchy tracks below the whole goal. But Reacher barely moves. Both planners stay high across every horizon. This one figure explains both. Solid is the planner's latent cost, dashed is the true physical distance. The cost flattens almost immediately while the real distance keeps climbing. So past a short range, the planner scores every candidate with a dead signal. It's effectively blind. Two rooms goals leave that zone so it collapses. Reacher only looks robust because its goals stay physically tiny. It was never really a long horizon test. So where's the problem? It's not the macro action encoder. A probe recovers motion at r squared equal to 0.89. The problem is the cost. Latent distances only track real distances up close and then it saturates. The macro planner ranks subgoals with the same flat signal, so it inherits this blindness. So the fix is in the representation and not the planner. A distance-aware cost or training the encoder jointly with the hierarchy. The hierarchy idea isn't what failed, it was the cost which was at fault.